Okay. So last time, I think we finished at we were discussing different classification algorithms, and by the end we had finished discussing about random forests. Or were the discussion of random forest pending?
Yes, a little bit of random
Let
forest.
Oh, okay. So let me then open up our PPT. Then we'll come back to it. So, we discussed entropy. Hmm. Okay. Did we not cover this? I think we covered this. Anyways, we can quickly discuss. So decision trees we are uh, somewhat clear. Maybe I can quickly summarize. And within decision trees, what we do is, again, the whole task of machine learning is to learn the underlying space. And within the underlying space, the idea was that once we have a data like this for decision tree, we are interested in coming up with a tree using which we can traverse. If we know for each feature what is the value we have, then we can traverse this thing. Okay. So, like for in this case, if we go for, let's say, any of the rows here, like row number 11, it says what is the outlook. If it is rainy, we come to this path. We check for the next state, which is humidity, and humidity, if it is normal, we go to yes. So the answer comes to yes. So we said, okay, such a tree would help us in identifying or knowing for unseen cases. The question is, how do we create such a tree? The way decision tree works is it works on the system of entropy, and we say depending upon what is the entropy, we'll be able to know what is the chaos within the system. So decision tree, basically you are trying to subset different areas so that within each space we have all similar classes. So we said, okay, for this decision tree requires two kind of entropies. One is just with the target. Second is with the attribute. And we saw how to evaluate entropy with the target, how to evaluate entropy with uh, the target and an attribute. And we come up with these numbers. So again, based on these two values, we talk about something called as gain. And gain is much more natural to imagine. In sense of gain is something more the gain of a attribute and a target. It means if we split using that attribute, it will be the best for us. Okay. So we said, okay, this will be the procedure for evaluating the uh, tree. That is, we calculate entropy of the target. We split the data set based on different attributes. So we'll calculate basically the gain for each of the different attributes. We choose the attribute with the largest gain. And if after dividing, we have entropy as 0, we end up with the leaf node. Otherwise, we say that we need further splitting. Okay, this algorithm is called ID3, and we recursively run this algorithm till all of our non-leaf branches is split. Okay. So yeah, this was decision tree. Let me go ahead. Okay. So given this background of decision tree, we said that okay, how or what would a different algorithm called as random forest do? Okay. So random forest is an algorithm very similar to decision trees, and it works on something called as ensemble methods. So ensemble methods are where you don't have just one algorithm running; you've got a combination of multiple algorithms running. And we I think we started to discuss on what is the advantage of something like this. So the primary advantage of something like this, that is, we have when we have ensemble algorithms running, is that we say that the wisdom of crowds is better than the wisdom of one. Okay, the wisdom of crowds is better than the wisdom of one. So by a wisdom of crowds, we mean that if we have just one decision tree giving an output, instead of one decision tree giving an output, if we have around 10 trees giving an output, it would make much more sense. And 10 trees giving an output mm, uh, will not, or we have to ensure at least that the 10 trees are different, they are varied. Uh, just replicas of the same tree giving 10 outputs makes no sense. We need 10 unique different trees, 10 different trees to make out the output. And these unique trees, we said, how do we decide that they are unique? So we said, okay, there should be some kind of randomness. So we have two methods like this, bagging and featured randomness. And bagging is where let's say we have 15 items that we train with. We will choose 15 items with replacement, with bagging. So it may happen that we choose with multiple copies of some items and some of the data does not go to that tree. Uh, and in that sense, we can create bagging, and this would create some kind of randomness between the data, ensuring that your trees are a bit different, because we saw that even with single data points, your tree may require a split or not. So when we move data points here and there, it ensures that we don't end up with the same tree. So we get unique trees, that is one part. And feature randomness. The way we get feature randomness is when we are splitting based on attributes, we will not allow the algorithm to choose certain features. So it is forced to depend upon only the remaining features that are there and then get some, that will allow some feature randomness. Okay, now I think I remember why, what was the next step here. I think I had started to talk about uh,
Underfitting, overfitting, and
yes,
all.
overfitting, underfitting, and this. Okay, yeah, so that is where we stop. Okay, great. So, okay, talked about high biases. Let me then shift to my iPad so that I can draw some things. Yes. Had I started this thing, I would have known instantly where we were. Okay, great. So this is where we had finished our discussion last time on overfitting, underfitting, and dogma fitting. So before going ahead, can uh, have you heard these terms before associated with machine learning at least? Uh, Underfitting, overfitting, and normal fitting.
Yep.
Okay. Can you try to guess what do we mean by that?
Okay. Underfitting is like our training data is not good enough, so we are not able to catch the variations.
Okay.
Overfitting is like our training is too good. It is taking all the variation, including the noise or something outside, which is not relevant. Also, it is catching.
Mm-hmm. Okay.
That is overfitting.
Okay. Yeah. That's pretty much it. But I will
Yeah.
add
You
some
won't
more.
explain me. That's the difference.
No, no. You rightly said. You missed some parts. I rightly explained both parts. Okay. The thing is, explaining overfitting and underfitting, is much easier if we explain through a regression problem rather than a classification problem. Okay. So just for the sake of this explanation, I will use regression data, and I hope we'll still be able to catch up with some of our background that is there. So let me present some data points like this. Okay. And let's say our data changes this way. Okay. So let's say this is our data. Let me create 3 copies of this. Okay. So So this would be our underfitting. This will be our overfitting. This would be say maybe normal or perfect fitting or whatever. I don't think there's a term for this. Neither these things. We also talk about something called as bias and variance. This would be high bias, low variance. This will be bias, variance. This would be low bias, high variance. Okay. So, thanks. In the first graph, can you tell me what is the problem with the first graph?
It won't catch all the points.
Yeah, why will it not catch the points?
Because our model considering a straight curve, it is not taking that degrees properly.
Yes, excellent.
It is
So,
x equal to y, not x equal to y square.
yes. So here, in the first case, not that my data is less. In fact, in all 3 cases, my data is similar. In the first case, the model that I'm trying to fit is not right. The data requires a more complicated model, whereas I'm trying to fit a model that is very simplistic. Okay? So in the first case, let's say I could say that I'm trying to fit something like y is equal to theta naught plus theta 1 x1. The second case, I would say I'm trying to fit y is equal to theta naught plus theta 1 x1 plus theta 2 x2. Okay, or let me, since we are just talking about one feature, let me get rid of the indexes here and talk in terms of indexes here and talk in terms of squares, theta 2 x square. And in the third case, my model is something like y is equal to theta naught plus theta 1 x plus theta 2 x square plus theta 3 x cube plus theta 4 x to the power 4 plus theta 5 x to the power 5. So here I have 1, 2, 3, 4, 5, 6, 7, 8 also. So I would have at least 7 terms here plus theta 6 x6 plus theta 7 x7. Okay. So this would be the different kinds of model that we are trying to fit for the same data. Okay. Same data. We're trying to fit a very simplistic model. which is taking only two coefficients. So these two coefficients can only capture two things. One is what is the intercept on the y-axis, where it is intersecting. So here, this is the value. And the second is what is the slope of this curve. So we clearly see that our data is going parabolic. Okay. Why can we clearly see that? Because we have, at least in this case, we have the ability to visualize this data. Okay. So since we can visualize this data, we can see that the data goes like this. So we can say that, okay, this data cannot be fit using a single line. And as verified using this plot, we can see that it does not fit well. But since we can see the data, we have said, okay, if I use up to power 2, I may have a good fit. And here, okay. So first we discuss about this, that this is not a very good fit because my model does not have enough variance to capture this data. Okay. Can you tell me why this data, why this fit is a problem?
Because it's overshooting at few points because of this noises.
Yes. So because of this thing, this thing, this thing, this thing, and so on, right? So in fact, I have drawn this very conservatively. Ideally, I should have drawn something more like this. Okay, let me. So, so what we see is, even though this graph, it hits through all of the data, it connects all of the data. It is not actually it is very good because it is. If you look at the error of this graph, the error of this graph will be minimal. Okay. What is error? By error, I mean what is our actual prediction, what is our actual data, and where is our prediction. So if you take, this is the error. In this case, error is this much, this much, this much, this much. So my total error is I have to square all of these errors, sum all of these errors, and find what is the error here. I can find what is the error here. I can find what is the error here. In this case, I will have no error because what I'm doing is I'm touching to all data points. My prediction and my actual data, they are aligning very nicely. Okay. So in fact, what I will get is I will get highest error here. I'll get some error here. Let me make a this, and I will get error is equal to 0 here. Okay. Still, I would say, even though error is 0, this model is bad because, as Anand said, uh, the points where there is no data, my model is going very high. Okay. And what is the purpose of training the model? The purpose of training the model is that when I give unseen data, this model should give a estimate nominal to what we have been training with. So in this case, if I say that my unseen data is something like here, let's say uh, this is the point where I say if someone gives this x, what should be the value of y? So what this overfitted model will do, it will go, okay, let me go to the model. It will say, in this case, either here or here. So let me take the bad example where it will come to this point and say that this is the value that we have. But we know that our model, truly looking at this, my value should not have been anything greater than this. Okay. This would have been the actual good value to answer. And a normal fitted model will give us that answer. But an overfitted model will not give us that answer. Our overfitted model will actually give us a very optimistic output or very pessimistic output, depending upon your luck in which part of the which part of the overshoot you are. And we say that this is the problem with our overfitted data. That is, my model is actually so good that it is only usable for my training data. For my unseen data, this model would be very bad. Whereas this model would do good, even though it is not, it still has an error. That is, it is not touching all of the points together. This graph, this line is able to capture the essence of the underlying system, and that is what is more important. Does that make sense? Okay. So we talk about three things: underfitting, normal fitting, overfitting. We also talk about the same idea with relation to two terms called as the bias and variance. Okay, a model here that is that is not sufficient to represent the data is said to have a high bias. Okay, this is said to have a high bias, and it is also said to have a low variance. So the way I remember this is, this model is so biased that I say that this equation is sufficient. And what actually happens is this sufficient does not, this equation is not sufficient, and thus I have a very high error in my model. That is what high bias means. Low variance in the sense of I don't have much variation. Whereas here, I will say that I have very low bias, but I have high variance. So I have high variance within my model, and that is a trouble that causes me to overfit. Anyways, for me, it is very difficult to remember. If you just tell me high bias and variance, it is difficult for me to measure which one is what. So I always try to think about underfitting, overfitting, and based on that, come up with what should be the bias and variance for a model. Okay. Okay. So I have also written some equations for each of the cases, and we see that we can see the complexity of the model, and based on the complexity of the model also, we can decide, or we can say if we have chances of underfitting, normal fitting, or overfitting. Okay. So in this case, we we said that going till two terms, that is having the base term, the uh, power one term, and the power two term is enough. Okay. Can you tell me in a general scenario, how would we know how much is enough? As I said, in this we could see the plot. Okay, but let's say we don't have access to visualizing the plot, which is very much a scenario because for data science you may end up with high dimensional data. Let's say there are 5 or 6 features, then it is impossible for us to visualize the data and find out how the data looks. So we will not be visually we will not be able to identify or shortlist the number of features that the number of the complexity of our data. So in that sense, we need to have some other measure where we can find out if power 2 or power 3 or so on is enough or not. Does that make sense? Okay. Do you have any guesses how this will work out? Like how can we know how complicated our model needs to be?
After training, by doing validational testing, we can get that.
Yes, excellent. By doing validation and testing. What would be the strategy for checking validation and testing? So yes, it's okay. I'll answer
Yeah,
this
I
one.
don't know. Yeah.
So what we can do is at every training step, we can check for two things. So generally, most algorithms, they have an iterative learning. Okay, so you will do one step, you will see how it works. Then you'll go to the next step, you'll see how it works. You go to the next step, you'll see how it works, and so on. You will slowly start to iterate it further. Okay, and we are looking for two waveforms. We're looking for something called as training accuracy and validation accuracy. So training accuracy, I would expect like this. So as I go more number of iterations, so let's say on the x-axis, we have iterations. And on the y-axis, we have accuracy. Okay, this will be iteration 0, iteration 1, 2, 3, 4, let's say some iterations. Okay. So we see that in the first case, our training accuracy, it's at iteration 0, we are somewhere here. This is, and then slowly iteration 1, iteration 2, iteration 3, so on. So we generally go on increasing in terms of accuracy. Okay? And let's say this is your 100%. So training accuracy will generally go on increasing. As you train more and more, your model will learn more and more about your training data, and thus it can do more and more good. So that would be your training accuracy. On the contrary, my validation accuracy, that is at every step, if I check at the validation accuracy. So validation data is the data that my model has not seen, and what is the accuracy for that data is actually the true test rather than training accuracy. Validation accuracy is a true test of identifying what is happening. So we will observe validation accuracy, and let's say our validation accuracy goes like this. First case, over here, it also maybe stays same for some time, increases for some time, but after a certain time, it starts reducing. It starts reducing, and the place where it starts reducing, this gives us an idea that this is the peak point of my estimation. Training the model more than this point would actually overfit my model. Why? Because how do I know I'm getting overfitting? Because my uh, training accuracy is improving. Even after this point, it is going ahead, but my validation accuracy is going down. It means that my model is becoming more in tune with the training data rather than the nominal behavior of the normal data. So we look at these two terms. Let me write this here. Validation accuracy. Validation or testing accuracy. And this will be my training accuracy. Does that make sense? Okay. Yeah. I think we will stop discussing on overfitting at this point. Maybe later I'll present in more detail, especially when we reach towards our regression part. And there is also one part that I need to discuss, something called as optimization. And during that time, I'll discuss more about our accuracy and how do we look at it. Maybe now we can go to our Titanic dataset where we had last stopped, and from that point onwards, we will try to implement some machine learning using scikit-learn to be able to see how we can use those ideas for an actual set. Are you able to see my screen? Yes. Okay. Just give me a moment. Okay, I'll quickly summarize our Titanic. In either cases, I have to run the model because I've just opened this. So we had used the Titanic dataset as our example for doing data pre-processing, and we have different features. So these are the different features that we have: embarked, cabin, fare, ticket, parent, children, sibling, spouse, age, sex, name, passenger class, survived or not, and passenger ID. And we are interested that using everything else, we are supposed to predict for test data. We're trying to predict whether someone survived or not. Okay, so that was our idea. We went ahead and we did all these steps to know more about the data, to find if there are missing values or not. We added some visualization to see what is the correlation between male, female, what is the correlation between passenger class, survived and dead. After all this analysis, we also did some feature engineering. That is, from our name, we tried to extract the title, and based on title, we did something like this. For Mr. we said 0, Miss we said 1, Mrs. 2 and 3. Can you tell me what is the process we did so far? So taking the title and assigning these numbers to it, what would these steps be called?
To load to train, we have to convert all the characters to a number.
Right.
I don't remember its particular name, but this is the thing we did.
Yes. So here it would be called, I think, binning, because we have, based on the different names, we have binned the data in different sets. Okay. We have binned into actually 4 sets: 0, 1, 2, and 3. So this would actually be a good example of binning. Going ahead, we did the same for test. We did it for male, female. Age is also something that we bin together. We merged 2 features together. Yes, and okay. So by this point is where we had left. Okay. So after doing all of our stuff, feature engineering, pre-processing, we left with this data. We left with train data, and from our train data, actually this is what our train looked at this point. From this train, and this is test, we from the train we removed the survived category and popped it out into a different variable. So here you can see that I have copied copied the column survived into a variable called as target, and from train we have dropped survived and we are left with train data. Okay. So here now we have 2 data sets: train data, which has these columns. So we have also removed passenger ID from this, and we have test data, which is having these items. Okay. Yes. Do you have any questions before going ahead? Just any question on pre-processing or something like that? Okay, great. So we all are clear that how we get our pre-processed data. Once we have our data, the next more interesting thing to do would be how do we train with multiple algorithms. So we in this case we'll check for nearest neighbors, decision tree classifier, random forest classifier, Gaussian Bayes, naive Bayes, and support vector classifier. So all of these classifiers we are loading from a package called as scikit-learn. Okay, so scikit-learn, the way we import it is we write sklearn, and then we have to look at which module that that particular classifier may be. So not everything is available in one place. So as we go and do multiple algorithms, you will find out that each of them have their own independent module. Like we can use k nearest neighbors for classification or regression or so many things. So they have distributed it in modules, and we'll have to load from each independent module. So in our case, in the first case, I just load all of these classifiers together. Say we do train info. We also call something called as cross-validation, k-fold cross-validation. And I think we have discussed k-fold cross-validation also. The advantage of this is instead of just having a 3-fold split between our data, that is taking our data and dividing into train, validation, and test, if we take our train data and if we do something like cross validation, we get a more robust, more accurate measure of how good our model is doing. Our model is able to see all parts of our data, and it spits out, or it gives us as many accuracies as there are folds, and for each of the mean of that can give us the sense of how good or bad our model is doing. So in this case, that is available from sklearn.model selection. We import k-fold, and k-fold is something that splits our model, and we call something called as cross-validation score. And cross-validation score is exactly what it does. It does cross-validation between our data and between the folds as input. Okay, so we take k-fold and we say how many splits are we interested in. So here we give number of splits as 10. Shuffle is true, and random state is equal to 0. So random state generally you can keep any value here. What it just means is the next time when you run this model, if you want the same output, you use the same random state. Okay. Apart from that, not much meaning to random state. Okay. So we run this, we get k-fold, and here I'm calling k neighbors classifier, and I'm passing an input of 13 neighbors. Okay. So just randomly I'm saying that let me use 13 neighbors. There is uh, no sense to choosing this value, and there's actually a better way of doing this, but for now, just to demonstrate our algorithms, we can just put some number and see how it works out. So I put 13 neighbors. We get the classifier into this place called as CLF, which is our classifier. We choose what is our scoring methodology. We're saying, okay, for our case, since this is a classification problem, maybe accuracy is a good measure to know how good or bad we did, which is accuracy is a good measure only when you have a balanced class. But so far, since we are starting out, I think accuracy is fair enough. We can put that as our scoring method. And we're calling this function. We are calling this function cross-validation score. And to this, we give our classifier as input, we give our train data, and we give target. Okay. So train data is our X, that is all the features, that is tuples of features, except for the target class. And then we provide the target, which is the label zeros and ones. CV is, we say, how do we want to do cross-validation? So we say, okay, we want to do cross-validation using k-fold, which is what we defined here. Actually, within CV also, you can put a number, and that can do our cross-validation splits here itself. But providing it using k-fold gives us some more advantages. So later on, you'll see you can divide this in a stratified fashion or not, and so on. But I think for now, we can just say, okay, for cross-validation, just take k-fold. N jobs is the number of processors we should use in solving this. So my system is an 8-core machine. So when I put n jobs as 1, out of those 8 cores, it will only use 1 core in the working here. So for this case, it is fine because our data is really small. But if you are going on tens of thousands of data, or if you're training maybe hundreds of models, then either of the case, when a system is computationally intensive, I would want to choose n jobs as something called as -1. And what n jobs as -1 will do is it will use all the available cores. So in my case, then it will use all 8 cores. It will divide the task into multiple parts, send it to your 8 processors, operate upon them, and combine the answers and give us the output. For now, we'll just keep it 1. We'll come to a case later on where we actually need to do this, where we have hundreds of models to train. In this case, not so much, it's fine. And we say, okay, a scoring method will come from the scoring method. These are all the inputs that you would want to give to cross-validation score. The output we are collecting into score. So this score will be 10 different values because we have a 10 split cross-validation. So when I execute this, this is what k nearest neighbors gives as our accuracy. Okay. So for our first split, it is said that it was right 82% of the time. For the next split, 76, 80, and so on. We are more interested in probably what is the mean accuracy. So if we take all of these numbers and find its mean, so we can easily do that using our NumPy package. So np.mean of score, just get a neat number, so multiplied by 100 so that we have it in percentage form and write up to 2 decimal places. When we execute this, we see 82.6. So k nearest neighbors, KNN, is able to give us accuracy of 82.6 with our data. So Okay. Can you tell me what accuracy this is? Is this train accuracy, test accuracy, or validation accuracy?
Validation accuracy.
Okay, yes. So this would be cross-validation accuracy, which is fair enough, because we are taking each of these cases and we are able to find out what the accuracy is. So had we done this split ourselves, that is, instead of calling cross-val score, if we had divided train further into two parts, then we could check manually what is our train accuracy and what is the test accuracy. So I think here cross-val score, maybe not here in Crossvalidation Score. When we do something called as grid search, we have train accuracy and validation accuracy given separately as numbers. I don't know if we can extract this from Crossvalidation Score. Let me quickly check. So if we do help of Crossvalidation Score, let us see that does it return to us train accuracy. Okay, we have a verbose level. Fine. No, it just returns to us scores of cross validation. So we cannot find train accuracy using cross-validation score, which is fine. Later on, we'll have another method which is able to give us at each step what is the train accuracy, what is the validation accuracy. Okay, so this gives us 82.6, which is fairly good enough, right? Do you remember what accuracy we were getting by just using our model of in the initial case we had estimated let all females survive and all males not survive, and we had estimated an accuracy.
Around 60%, I believe.
Yeah, around 60%, right? So, which was a fairly a good estimate, but now we have a much better estimate, and the reason it is much better is it is able to take into account more features and more processed features rather. So we have done a lot of processing that has allowed us to see more of the data better, and it takes into account all these quantities, and based on these quantities KNN, we have also seen how KNN works now, so we have a fair understanding. In the background, KNN would have calculated the distance from for each of the validation data set. It would have calculated the distance with each of the trained data sets, and based on that distance it would have sorted according to the closest ones, and we have put K as 13, so it would take uh, the 13 closest neighbors, and from that see how many of those neighbors were uh, survived or not, and based on that it has done estimation on our validation data set, and after doing it for all points we are checking the accuracy. So KNN gives us 82.6. I think fairly good enough. Let us go ahead and see how we would implement decision tree. So we call the decision tree classifier that comes into CLF, and that's it. That is the only extra thing that we are doing. We are calling over that cross-validation accuracy, cross-valid score. It does the cross-validation, gives us the score, and we get something like 79.46 as our accuracy with decision tree. If we do it with random forest, we are just calling random forest classifier with 13 estimators. So 13 estimators means it will call 13 different, it will train 13 different trees for random forest. We can maybe try a bigger number as well. Let me try 30 trees. And with 30 trees, it gives us an accuracy of 80.47. And we know naive Bayes, we call naive Bayes. So naive Bayes works on probabilities. That gives us 78.78. And we have something called as SVM, support vector machines. Support vector machines, uh, they work on the idea of support vectors. That is the boundary line that divides between the two classes. We will look at the closest data there, and we'll use them to create the highest margin that is possible. Okay. So That's okay. So that's a different algorithm. And I think of all these, our support vector machine is giving us our best answer, 83.5. Naive Bayes, and Forest, Decision Tree, and Kane. Okay. So Kane is the second best with 82.6. The first is SVM. So we said, okay, let's say we have trained our models and SVM gives us the best classification. We will choose SVM to or in this step where we tried different algorithms, we are shortlisting which algorithm will go good. And let's say with our base satisfaction, we are saying SVM is the best that we have. It's okay. Now, how do I deploy a model? So I will retrain my model. Can you tell me the purpose of retraining my model? Why do we have to retrain our model? Any guesses? At this point, we have trained our model nonetheless, right? So we have loaded SVM. We have SVM in this classifier. We have seen this is working well. So I have a trained classifier. Why can I not use this classifier directly for prediction? And I need to retrain my model. So maybe I'll give the answer to this one. So at this point, we are doing something called as cross-validation. And for cross-validation, we are using 10 folds. So at each fold, I have 10 different models which are trained from different parts of the data. I don't have a model which is trained from all of the training data. So we use cross-validation uh, just to figure out which, uh, how good or bad our model is doing. But once we want to deploy our model, we would want to train with all of the data. So here, each model is trained with 90% of the data, but now we want to train with 100% of our data. That is why we have to retrain our model before deploying it in the test environment. So here we load support vector classifier CLF. The way you train your model is calling the dot fit function. So CLF dot fit will train our model, and we will train with what is the X is the tuples of data, and Y, which is the target. So we give these two to it. With this, our classifier is trained with all of our data. And for test, what we have done is from test, we have dropped passenger ID. We have dropped passenger ID because, okay, so here test data, what we have done is we have created a copy of test by dropping the passenger ID. And that is our test data. So this test data should look exactly like our trained data. It should have the same, features. It should have the features in the same order as well. Because the classifier does not know the difference. The classifier is not like pandas. It does not read the column names. It is interested in feature 1, feature 2, feature 3. So we put that into test data, and then we use the classifier that we have trained here to predict it. So we call clf.predict on test data. That gives us our prediction. Okay, so when I execute this, let me see our prediction. If I write prediction, we have a series of zeros and ones. So this is what our model is predicting for each of the features. So which features? So I say I do test data.head. So let's say for our first 5 rows, for this data, passenger class 0, sex 0, age 2, fare 0, cabin 2, embark 2, title 0, and family 0. Our model has said that this passenger has not survived. Okay, and for this passenger, it says it has survived, and so on. So like this, we are getting a prediction for each of our cases. Now, as I said earlier, this data was taken from Kaggle, and Kaggle has a certain form in which you can upload the data. So it says that we have to upload in something called as a CSV, submission.csv. That CSV needs to have a passenger ID column and a survived or not survived column. So we take that, we take our prediction, and we load our prediction into a data frame. So pd.dataframe, we create a new data frame with 2 columns, passenger ID, which comes from test passenger ID, and prediction, which comes from this variable. And once we have it in a data frame, we can send it to a CSV file by writing submission.toCSV. Okay. To read the CSV, we use read CSV, and to write to a CSV, we write to CSV. When you write to CSV, it would have created a file within my present structure. So let me execute this. And if I do ls, I can see that it has created a file called as submission.csv. I can verify that by loading that file again. So I'm reading that file again into a data frame submission. And if I look its head, you can see this is what our data looks like. Sorry. Okay, so this was just basic training the model. What we have done so far is we have discussed these algorithms. We have a fair understanding what is their background, and we have trained our model with this. Can you tell me what is the part that is missing? Or what would you want to do more with the prediction before actually finalizing on a model?
Do the testing. We just want to see how much it is matching now.
So testing actually in this terms we cannot do, because the test data that we have
Okay, we got from Kaggle.
So Kaggle is a competition environment. So here, the only way we can find a test score is we upload this data on Kaggle and we see what is the score Kaggle gives us. Okay, and Kaggle also will not give us the full score. I think since Titanic is a play data set, it may give us the full score. But generally, the score that Kaggle gives is divided in two parts, on a public set and a private set. And it reveals to us only the public set part of the score. And that will be displayed on the leaderboard. The other part will not be shown. And only once the competition finishes, they will say what is the final score. But this is fine. Normally, if I would want to do testing also with my data, or want to do testing score, I will take the known data that I have and divide it into two parts, train and test. And the train part, we'll do cross validation with that, and test part is something that we will measure to test it. Okay, but apart from this, what else is missing? Okay, so if you remember, while our discussion, we said that each of these classifiers will have certain things that we can control. Like for k neighbors, we can control the number of neighbors that we have. So here we have randomly chosen 13. 13 may not be a good answer, and by choosing maybe better number of neighbors, we may have ended up with a much better accuracy. Similarly, decision tree, we have not given any options. So decision tree has multiple inputs that you can provide. If I just quickly check, if I do help over decision tree classifier, I can see that there are several parameters for the decision tree. So I can control the criteria for splitting as entropy or Gini. So by default, it is Gini. So Gini is a similar score like entropy. In either case, we need a measure of chaos. We need a measure of impurity of the data. So by default, scikit-learn has chosen Gini. We could choose entropy also. So this is one option that we could have tried. So splitter, it says the strategy to be used to split at each node. We have two strategies, best and random. By default, it is best. Max depth, how deep are we allowing the tree to move? Okay. So when you say none, then, or the default is none, basically what it means is it will go on till that depth where all the leaves are pure. Okay, till it has not reached that point, it will continue splitting. But we can also choose what is the maximum depth. So let's say if we keep the maximum depth as 5, it will not go below 5 nodes. Okay, so how does this help us? Let's say by controlling maximum depth, what can we ensure is not happening is we can choose, by choosing a lower maximum depth, we can choose the complexity of our model. And by choosing the complexity of our model, we can prevent overfitting. Okay. So again, this is an option that we can try.
But small doubt, if we limit it with 5 or 6 or whatever, Then if we didn't achieve that two categories at the end, then what will happen?
So can you tell me if I limit my depth to let's say 2, how can, and I may not have a pure set, how can I do my prediction? What would be your just throwaway answer?
In that, which they just guess something.
Yeah, based on
What are they have as of now?
yeah
Maybe,
based on majority, right?
yeah.
So you made a split, and after the split, you have like say 91 data saying like you have 6 examples saying survived, you have 5 examples saying not survived. So you will go with survived. So that is what will happen when you limit the depth. Okay, but still it is to some extent even that is good enough depending upon our case, right? So overfitting is a serious problem, and we at least have some level of control by choosing the depth part. So that is with max depth. We have minimum sample split, then we have minimum samples leaf, we have minimum weight fraction leaf, max features, which can again take 3. This is a categorical parameter taking auto, square root, or log 2, and some default, random state, max state. So we have lot of options that we can play around with. Let's say for each, so here I can see at least maybe 10 different options. Okay, and even for 10 different options, for each option, let's say you tried 2 different things, so we'll end up with 2 raised to 10. Is that right? Yes, for each option, if I try 2 things, I'll end up with 1024 models, 2 raised to 10 models. Okay, so here we just took the most basic default version and we trained it. Maybe if we control some of these aspects, we could have gotten a better accuracy from decision tree, much better than 79. Okay, so that would change the model that we are choosing for our data. Okay. So we need to have a better method of doing that, and I think in the next class I'll focus on this part. We call it something called as grid search, and the idea of grid search is not just finding the uh, training parameters, but we're also interested in the hyper parameters. That is, what are the parameters that we can control for the classifier at hand, and how we can train it with those options. Does that make sense? Okay. So next class we'll do that. Do you have any questions before we stop for today? Okay. Okay then. Great. Have a good day. Bye bye. We'll meet back on Monday morning.
Bye.
Bye. Bye.